All right, guys, so we're doing logarithmic functions and exponential. So today is going to be exponential. Okay, we're not going to use that nice fancy log button today, but we will. But we're going to do exponential functions today. So we're actually going to cover two sections, both 7.1 and 7.2. There's a lot in here, so hang with me. But they flow nicely together, which is why I put them in the same section today. It's all about exponential functions. All right, so a basic exponential function is I have two things being multiplied and one of them has an exponent. Makes it an exponential function. Okay, there are some stipulations. A cannot be 0. Why would A not be allowed to be 0? Because then it's just 0 and that's not very fun. B has to be greater than 0. We want it to be a positive number. And B also cannot be 1 because 1 to any power is just 1 and that's not very fun either. And x can be any real number. Positive, negative, decimal, fraction, whatever, it does not matter. Just it has to be real. Okay, so let's kind of take a look at what a graph of an exponential looks like. So we're going to graph half times 4 to the x power. So we're going to go old school here. I know we can graph it just with the calculator. Let's go old school and kind of plot some points just so we can kind of see what's going on. So typically when you're plotting points, where do you usually start? I heard whispers. Where do we start? 0 is not usually where I'd start. That would probably go about halfway through my list. Yeah, I'd probably start -2, -1, 0, 1, 2, just because that way I can see kind of on each side of that axis, positives, negatives, kind of what's going on. So let's go ahead and plug in a -2. So what is 1/2 times 4 to the -2 power? What? You have a calculator. Come on, guys. What is half times 4 to the -2? Point, what'd you say, 0, 3, 1, 2, 5? Is she right? Yeah. Fractions is your green button and then y equals and hit enter.
It's okay. That's not bad. I forgot my own lunch number.
I know, 2 weeks off, man. It's rough coming back. That's all right. It'll come back to us. We'll get back into it. What about if I plug in a -1? 0.125. Okay. How about I plug in a 0? I heard a 0 and I heard half. It's half. I'll go 0.5 since we got decimals going on there. What if I plug in, wait, did somebody say the 0 doesn't make sense? Anything to the 0 power equals 1. And 1 times half is half. All right, what if I plug in a 1? What do I get? That's 2. And if I plug in a 2, hey, there's numbers that we actually like to look at, right? All right, so if I plot some of this, so -2, and then it's just barely a positive number, right? And then I plug in -1. It's a little bit bigger. It's hard to do on something so small. 0 is going to be half. 1 is 2. 2 is 8. That's interesting. So what happens as it goes more negative? Is it going to drop below? It's going to go back up? For giggles. Let's not go that big. Go -10. Just so we can see what's happening. Did it drop below the axis? Should be 4.7. As I went back to -10, did it drop into the negatives? No. Is it really, really close to 0? Mm-hmm. So the further I go out here, the closer and closer and closer it gets to 0. It's never going to reach 0. Ever. So this graph So I'm terrible at connecting points here, but it's going to look something like that. It's an exponential graph. Isn't that fun? Those of you who will move on into pre-calc or calculus, this is where you would get into limits. You talk about limits in pre-calc and calculus. Limits is when it's talking about like it gets really, really close to something, but it never actually will cross that line and drop down below that, okay? So thinking about how this looks, this is what exponentials look like. Oh my goodness. Get out of the way. All right. So real quick, there we can kind of see what happens is the x-axis where it got really, really close to but never actually hit, that is called an asymptote. So you may want to kind of just jot that word down on your notes right here, guys. An asymptote is the line that it approaches but never actually crosses. It gets really, 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 really close. Kind of that whole 0.1, 0.01, 0.001, 0.0001, right? And you can just keep adding to 0.00000, stick a 1 at the end, right? It's never actually hits 0, but it gets really, really close. Okay, that's called an asymptote. So if you were talking about exponential functions, this is what's going to happen. It's going to kind of flatten out at one spot, and it's going to take off on another direction. Okay? All right, so let's kind of just practice with the calculator a little bit for me. So f of x equals 2 to the x. Do you remember what f of x kind of stands for? Y, right? You can use those interchangeably. So in other words, when I plug an x in of negative 3.1, what is 2 to the negative 3.1 power? Just getting a little calculator practice in here, guys. I know you had 2 weeks off, so we want to make sure we know how to use those still. So what do we get? That should be what you get. If you didn't get that, we need to figure out what we're doing wrong in the calculator. Round off the last 3 digits. Oh yeah, well, is this exact in your calculator? Is that exactly the answer? No, that's just how many digits my calculator held. Okay, that decimal keeps going forever and ever. Okay, it's not going to stop. So yeah, I just stopped at whatever point. So what about 2 to the negative x if x is pi? Find the pi button. Where's pi button located? Anybody find it? Yeah, it's above the caret.
Where's the carrot?
Right below clear. Your exponent button. The button you hit to make it be an exponent. That's called a caret. All right, so for that one, we should have gotten 0.1133147, and then there's more digits, but okay. And then what about 0.6 to the x when x is 3/2? All right, all of those are exponential functions because they have an exponent. Okay, exponential functions because it has an exponent. Easy enough. Kind of a real life scenario of exponential, radioactive decay. May have talked about this in a science class. In 1986, a nuclear reactor accident occurred in Chernobyl and what was then the Soviet Union. The explosion spread highly toxic radioactive chemicals such as plutonium over hundreds of square miles, and the government evacuated the city and the surrounding area. To see why the city is now uninhabited, consider the model, which this is talking about the plutonium, represents the amount of plutonium that remains from the initial amount of 10 pounds after T years. So you can kind of plug in how many years it's been and then figure out how much is still left. So if it started with 10 pounds, how much is still left today? And this was in 86? 1986. So how many years has it been? Well, this is 2020. 34. So my t-value needs to be 24. It's been 24 years since that happened, or 34, not 24. It's been 34 years. I got that 3 that you mentioned in my head now. 34 years. A lot of it should be gone by now, right? How much is left? Did you say 9.99? So it's been 34 years. So do you think anyone's moving back in anytime soon? No. No. But that is an exponential function. Is that exponential growth or exponential decay? That would be decay. Very slowly. Okay, but it is eventually, it's getting smaller. But it is an exponential function that we use to kind of figure that out. All right, so there we go. So we have growth and we have decay. Exponential growth is going to be the one that we graphed by hand, right? Because we read from left to right. So from left to right, it is going up. It is growing. All right. Now, to tell if it's growth or decay, we can look at just the equation and be able to tell. For growth, if your the a value has always got to be bigger than 0, but if your b value is greater than 1, so that is the number that is being held to an exponent. If that number is bigger than 1, it is going to be growth. And if that b value, again, the number that has the exponent on it, if it's between 0 and 1, it's going to be decay, because that number has to be positive. So in other words, if it's a decimal or a fraction that's less than 1, it's going to be decay. If it's bigger than 1, it's going to be growth. Can it be 1? 1 to any power. Is that very exciting? No, it cannot be 1. Okay, it has to be greater than 0, but it cannot be 1. Okay, so bigger than 1, it's going to be growth. Between 0 and 1, it's decay. So you should love those questions on a test. Identify if it's growth or decay. How about the first one? Again, always looking at the number that has the exponent on it. That's between 0 and 1, so this is decay. And then this one, this is growth. Can you see where people might mess up those two? Because if I look at this number, it'd be the opposite. I don't care what this number is. It's always the number that has the exponent on it that we look at. Okay, what about a story problem? Your parents put $5,000 into a college savings account when you were born. It pays 5% interest per year. Is that growth or decay? Why?
No, it'd be a decay because of
0.5 is 50%.
Oh.
Okay. I'm glad you guys brought up some things. It is growth. It is growth. But you're right. That is 0.05. You're like, but that's between 0 and 1. Why is it not decay? We're going to look at something that's going to kind of help you explain that. But this is growth, right? If you put money in a savings account, you're going to make money on it. You're not going to lose money in a savings account. Stock market, it can go either way. All right. So looking at this, you have our basic form, right? The a times b to the x. But we can kind of shift that. I still have my a, and this is my b. Instead of an x, I got a t. But right, I have some number. I have my b value looks a little different, and then I have the exponent. So in this case, this is going to come back to that same exact problem that was on that last slide. It's always 1 plus the rate. So 1 plus 0.05 would be greater than 1. Okay. The reason you need the 1 plus is because I want to actually include the $5,000 initially were put in plus any of that interest. So my final answer gives me my total at the end, not just how much interest I made. That makes sense? Okay. So here's your formula. I will give you guys a formula sheet because we're going to have a couple formulas today. But for this one, I have a plus or a minus in here. Why would I use a minus and not a plus if it was decay? right? Because decay would be 1 minus that percent, which would drop it between 0 and 1, which would make it decay. T is always in years. A is the initial amount, right? That first number, parents put in $5,000. R is the percent of increase or decrease as a decimal. Be careful, like not to pick on her, but she had said 0.5 was 5%. That's 50%. If you're not sure, how do you change them? It'd be 2 spots, right? Because how many zeros are in 100? There's 2. You can always just divide them by 100. If you're not sure, 5 divided by 100 will give you the 0.05. All right, so you invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much will be in the account after 6 years? So is this a growth or a decay? It is growth. So looking at my formula, so y equals, my initial amount was $1,000. And since it's growth, I'm going to do 1 plus. 5% is 0.05. And then my t, or my time, is 6 years. So we can just type that right in. Now, we are finding money, correct? So we want to go ahead and list it as money, which would be how many decimal points? 2. So what would I write on this one? 10 cents. It says 0.095. Remember, they're rounding rules, right? The next digit's 5 or higher, you round up. Doesn't make sense, what? Mm-hmm. It makes sense. Like change? Sense? Sorry, I was making a funny on what you were saying. I mean, that's $340 that you didn't have. All you did was let it sit in the bank. So it's not bad. All right, the Lorax population is decreasing exponentially at a rate of 13% per year. If the current Lorax population is 101, how many will be left in the year 2030? So is this growth or decay? Decay. So when I use my formula, y equals the initial amount was 101, 1 minus, because it's decay, and what's my rate? 0.13. How many years? 10. This is 2020. We're talking 2030. All right, so 101 times 1 minus 0.13 to the 10th power. So how many Lorax will be left? Should I have a decimal on this one? No, we're talking about a Lorax. You can't have. We don't want part of 1. So it's 25.09, so we're going to have 25 Lorax. Now, guys, kind of rule of thumb, thinking back to your younger math days, if it is a story problem, you need a label, okay? Now, a dollar sign can be a label. That's fine. But for this instance, I want 25 what? You'd have 25 Lorax. I will take a point off if you do not label your answers, okay? Yes? I think it's just Lorax. Kind of like deer. It's just deer. Moose. Mooses. Meese. Mices. If goose is geese, why doesn't moose meese? It makes no sense. No sense. All right. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. That's a huge increase every year. Write an exponential growth model giving the number n of incidents t years after 1996 about how many incidents were there in 2003. When it just wants the model, all you're doing, guys, is just show me your work. Just show me the formula. That's all I need. I don't care about plugging in random, just leaving it as variables. We know what the formula looks like, basically. Just go ahead and show me your work, plugging it in, and then tell me the answer, okay? So we're going to have y equals my initial amount, 2573. 1, is it plus or minus? Plus. It is increasing. Oh, it is increasing. Plus 92%, so 0.92. And then how many, my t value is what? 7. So they actually said the next 7 years. That's a lot. Whew, how many incidents were there? Ooh, not a dollar sign. I've been doing too much math problems today. So 247,485. We would round up to the next. What's my label? Incidents. Whoa. Why do you think it went up so much? Think about what year it was. 96. Think about kind of where computers were back in 96 compared to where they are now. And you know what I mean? Like, that was back when more and more people were starting to get computers in their homes and things like that. Really? Did not know that. Gotcha. Wow. So they've evolved over time. Are there more or less computer viruses now than then? They don't. The viruses today probably don't crash your computers as much as they used to. Gotcha. They're just stealing your information now. Makes sense. What? That's all right. The only one who would probably need to watch it is Ruben, so he can hear the whole conversation. All right. So guys, we talked about putting money in, figuring out how much money you're going to make, right? Leaving it in a savings account. Now, there are different types of ways that you can earn money at a bank. If you take the financial algebra class, we do a whole chapter on all about the different ways and all that kind of stuff, right? She knows how to do all that. But one of the ways is compound interest. So what compound interest is let's say I put $100 in the bank, right? And let's say it compounds monthly. Then I would put the $100 in. I would earn interest for that month. It would add it on. Let's say I earned $2. I don't know, right? And then the next month, I'm earning interest on $102. So then that month, I earned $3. So the next month, I'm earning money on $105. So it keeps compounding, meaning it's adding it on, and now it's earning on the higher amount. Adds that on, earns on a higher amount, right? Simple interest takes my $100. Let's say I earned, I don't know, $100, or not 100. Let's say I earned $10 that year in simple interest. So guess what happens for the second year? It's earning money on $100. 10 years from now, it's still earning money on $100. It's just simple. It's just on what you initially put in, that's all it ever earns interest on. Compound takes the interest you earn, puts it on, and now it's earning more. It's going to earn more because you're having more money in there. Does that make sense? So you want compound. You don't want simple. So when you're talking about compound interest, here's your formula. A is the amount you're going to have at the end. P is the principal amount or the initial amount that you start with. R is still your rate as a decimal. T is still your time. Then you have this N in here. Right? N is compounded N times per year. So if I tell you it is compounded daily, how many times per year is that? 365. If I tell you it is compounded monthly, how many times is that? How many months are in a year? 12. It's always per year, okay? What if I said it was compounded quarterly? Good, that's 4. Trying to think of other ways it might have mentioned it's compounded on there. It could do semi-monthly. Very good. Semi-monthly is twice a month, so it's 24. What if it's compounded bi-weekly? There are 52 weeks in a year, so if it's bi-weekly, it's 26. Went the wrong way. I know, semi-monthly is twice a month, but bi-weekly is every other week. No. Are those the same? Because there's not an exactly 4 weeks per month. There's always 4 weeks and a couple days. So that's why it's not exact. So what about weekly then? That's 52. You will be expected to know those. So you will need to know how many times it's compounded, if it's quarterly, monthly, daily, whatever. I could even tell you hourly, by the minute. That's not realistic, but I could throw it at you to see if you can figure it out. That'd be great, wouldn't it, if you earned money like that? It's not going to happen, but you know. Right? So you can do it. So she's got it. She's figuring it out. It's not that many hours when you really think about it. When you think about how many hours you waste just watching YouTube videos or scrolling social media, you know what I mean? Yeah. You waste how much of your life sitting at a red light? Then you may not have any life to even waste anymore because it's going to be gone. All right. So here we go. So $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it is compounded quarterly. All right, so guys, the way to tell what formula, because I'm going to give you a couple of them, if it says the word compounded, you're going to use the compound interest formula. Makes sense, right? All right, so if it is compounded quarterly, monthly, weekly, whatever, use that formula. So A equals, the P is the initial amount, so $12,000. 1 plus, what is my rate? 0.09 over N, quarterly, which means 4. And then it's N times T, so 4 times my time is 5 years. Now, real quick, I need to throw a little bit of caution out there. If you are using the graphing calculator, your life is easy, no worries, it will do exactly what you ask it to do. If you use a scientific calculator, if you're using scientific, don't write 4 times 5. Put 20. Okay? I just want to kind of throw that out there. Because what's going to happen, the scientific one does that caret button, and then if you do 4 times 5 afterwards, it would take whatever you had here, raise it to the 4th power, and then take that entire answer and multiply it by 5. That's not what you want it to do. You would either need to do separate parentheses around that, which is obnoxious, or just write 20, because it's not that hard to figure out. Okay? So everybody grab your calculators. Let's try this. Make sure we can all type it in, because I don't want you to not be able to use the calculator, and that's why you get it wrong. I think did you use the fraction button? That's why. The scientific does not like a decimal in a fraction, so just use division. It'll be fine. Just use the division. Now, guys, if you're using the graphing ones, the 4 times 5, the cursor stays up as an exponent, so it's not a problem. Yeah, again, scientific will not let you put a decimal in a fraction. You'd have to use the division key. All right, so you should get, double check, you would have $18,726.11. So that is how much money you'd have after 5 years if you just let your money sit in that account. That's pretty good. I earned over $6,000 in interest. How realistic is a 9% interest rate? Not at all. Not at all. But anyway, that's how that works. All right, so how much would this same investment yield if it were compounded monthly instead? So if it's monthly, what's the only thing that changes? Good. Yep. That n value, so 1 plus 0.09 over 12, and then 12 times 5. So remember that n is in 2 spots in that formula. Yes, but a lot more of this. You should see some of the formulas that they do in there. You don't have to memorize them. You get a formula sheet, but yeah. Yep, we do a taxes chapter. Yep, we do all that kind of stuff. Anything and everything you would need to be an adult on your own in the real world. All right, so what did we find, guys? Are we making a lot more or a lot less? Did you make more or less? Did you say more? $18,788.17. That's more. Does it make sense that it's more? If it's compounded more often, the initial amount it's earning interest on changes more often. It goes up. So yeah, the more it is compounded, the more money you will make. And then there will be more. I mean, it's not a ton more, but I don't know about you, but more money is more money. Yeah. All right, you deposit $4,000 in an account that pays 2.92% annual interest. Find the balance after 1 year if the interest is compounded with a given frequency. So you have quarterly and daily. Let me give you guys a minute and do both quarterly and daily. Okay? All right, guys, so let's go ahead and check how you did. So quarterly is 4 times a year, and how long are we looking at? How many years? Just one. So find the balance after 1 year. All right, so for quarterly, you should have gotten $4,118.09. Check your change, you should have rounded that. And then for daily, $4,118.52. But look at the time span. How long am I looking at? 1 year. Now, if I would look at 10 years, would I see a bigger jump in that? Yeah, you would. Yep. So obviously, the longer of a span I look at, the bigger of a difference you're going to see. But again, I mean, free money's free money. I'm not going to complain. All right, guys, we're going to shift gears a little bit, looking at something a little different. Fill in a table for each of the following values of x. Okay? So in other words, f of x, same thing as y. If I have 1 plus 1 over x to the x power. First time you do this, I want you to plug in the number 1. So 1 goes here, 1 goes there. Tell me what you get. So take a couple minutes. I want you to fill out all of these numbers right there. All right, guys. So looking at the table, the values you got, have you noticed anything? They're a bunch of decimals. But what happened as you went on with this table? So it's approaching, what's that thing called when it does that? An asymptote. Asymptote. Sounds like you're cussing at somebody, but you're really not. All right? But you notice, though, like it got closer and closer and closer to what would that asymptote be? What number is this? Did you know this number has a name? A name, so to speak? That number is E. E. Yep, E. So the natural base E is what it's called. It's defined as follows. As x approaches positive infinity. So as x gets bigger and bigger and bigger and bigger and keeps getting bigger forever, right? Then that equation I gave you approaches this number, which is known as E. You're like, great, why? Like, who cares, right? What's another number that you know of that we use a symbol to stand for it? Pi. Pi. Right? Pi is, what's pi?
2. Oh!
3.14. He said 2 point.
Don't get at
Right, but you guys know what pi is, right? Where does pi come from? The circumference of a circle, and it's not just the circumference. All right. No, I don't know, Mom. All right, guys, I just need to understand where these numbers are coming from. They're just not random numbers that somebody dreamed up one day, okay? Pi is the circumference of a circle, the distance around it, divided by the diameter. All circles. If you take the circumference and divide it by the diameter, you get pi every single time. Mind blown, right? You guys went your whole math lives and never known that, right? Any circle.
Is that why it's called pi?
I mean, that's just what they call it, yeah. But that's what the number is. So that number comes from an actual measurement. Same thing, E, it comes from an actual formula. As you get bigger and bigger and bigger, this number approaches this point, never is going to go beyond it. That's that asymptote that it's going to hit. It's at 2.71, blah, 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 blah. Will these digits ever end? No. Same thing with pi. Those digits go on forever. Okay? So let's go ahead and just get a little bit of practice, again, calculator based. F of x equals e to the x. So if I want you to find f of -2, what am I asking you to do? I have no clue. That was an honest answer. So if f of x is e to the x, I want you to find f of -2. Instead of x, I want you to put -2 there. That's all that means. So what's e to the -2? That's all I'm asking for. Yeah, what is e to the -2? Equals what? Yes, that's the great question. Where's E? Look on your calculator. Anybody see it? It's above the LN button. So if you look at your on button, 2 buttons above that says LN, it's above there. It says E to the X. E always has an exponent to it. So if you would hit second LN, notice it puts an E and automatically opens up your exponent. It always has to have one. So I would plug in -2 and see what you get. So let's do the first 4. So 0.1353. All right, f of -1. So I want to know what is e to the -1. So we should get 0.367, be 9 if I round it to the 4th digit. And then e to the 0.25. It's 1.2840. And then e to the -0.3. You get 0.7408. So do we know where the E button is? No, we don't? All right. So that is the number E. The number E. Sounds weird to say, doesn't it? All right, and you're like, great, where do we use that? The most common place that I can think of that we use the number E, that is exponential, right? It's a number that has an exponent automatically attached to it, is in the continuously compounded interest formula. Now, how amazing would that be if you are continuously compounded? So instead of them taking the interest and putting it on after a quarter or after a month, right? They're going to all the time. It's going to constantly be building interest, throwing it on top, constantly. So that amount that it's earning interest on is continuously getting bigger. All right? So I always refer to this one as APERT, P-E-R-T, APERT. Your principal amount you started with, E is a number in your calculator, and then your rate, which is always a decimal, times the time in years. Okay? So if you deposit $2,500 in an account that pays 5% annual interest compounded continuously, find the balance after each amount of time. So we're just using the continuously compounded formula. So my initial amount, my P, is 2,500. Then it's E. You don't substitute anything in for E. The rate was 0.05, and the time is 2. Now, when you're typing that in your calculator, you do not need to do 2,500 times E. You can literally just do 2,500 E. It will automatically pop it up to an exponent, 0.05 times 2. If you're a scientific calculator person, does it automatically open a parenthesis? Did it? Okay. So it's trying to help you out a little bit. All right, so after 2 years, you would have $2,762.93. Okay, how about after 5 years? What's the only number that's changing? Yeah, just that number up in your exponent, right? 0.05 times, now it's 5. If you're a lazy person like I am, I'm just going to go back up into my equation and change the 2 to a 5. Just if you arrow up, highlight what you want to use, hit enter, and it'll bring it back up again so you can actually change stuff. Yeah, highlight the entire part and then hit enter. Should have asked me a long time ago. So this one will be $3,210.06. Did you get it to work? Try it on the last one. And then for 7.5 years, so just arrow up, highlight your equation, hit enter, and then you can arrow in and change the 5 to a 7.5. $3,637.48. If you round off and your answers are off by a penny, it's wrong. So watch that next digit. If it's 5 or higher, make sure you round up. How are we feeling with all this? We're good? So this was all about exponential equations, right? It has an exponent. Things grow very rapidly with exponents on them, okay? Or decrease very rapidly. So these are the 3 formulas that you need. I did not put the basic exponential, the a times b to the x, because these are all a times b to the x. They just look slightly different, okay? So exponential growth or decay, it's going to be talking about something is either getting bigger or getting smaller. The value of a car when you buy it. Is it growth or decay after you buy it? That's decay. As soon as you drive that thing off the lot, it is decaying at a pretty rapid rate, actually. What about when you buy a house? It should be growth. As long as you take care of it, houses do get more in value, okay? So if it's talking about something growing, decaying, getting bigger, getting smaller, something, we're going to be using that formula. Now, if it's just talking about money, money's going to be one of these two, okay? Now, they both say compound in them. How do you know which one's which? This one is continuously. It will actually say the words continuously compounded in the story problem. That's when you use this one. Okay, if it does not say continuously compounded, we're going to go to this one. It'll say it's compounded weekly, monthly, whatever. Okay, and that's your end value here. Now, if you would like, I'm not going to help you do this, but if you want to write down on here, like n equals, for monthly is 12, weekly is 52, you can write those on there. I will let you put them on. Okay, so all the ones, if you took notes in class, you can go ahead and jot those off to the side or wherever so you have those to reference.